high school, and we are house, the goddess of intelligence.
Hello, everybody. We are team 1120.
And then I will ask our jurors to introduce yourselves. Please, starting.
那你肖家伟老师帮我们协同同学。
I'm just here academic senator.
This is myself, Cai Shangfang. For the introduction, you're allowed to use Chinese. Cai Shangfang from Taida Wulishi. Okay, thank you. The bells just rang, so it's the signal that we can start now. There is something which I have to remind you of. You cannot use internet whatsoever. You cannot make video recordings, none of you, okay? And please make sure that you don't put anything in front of the beamer or the projectors, which blocks the lights. Okay? So, okay, so that's all the few things I have to announce. Now we will start with the fight. First, I think it's the opponent. No, before that, let the, I think we should choose the comment and then we would write it down. Let the reporter, the opponent, challenge the report. That will be 2 minutes, 1 minute.
We would like to challenge question number 4.
Number 4 is what? Number 4, YPT, which is the unthinkable disk.
We are set.
So, accept. You have 5 minutes to prepare. At the same time, I think his team should write down the name of the person representing your team on platform. 跟那个对包括性，看到它然后结关于
所有我需要知道的资讯。
庆对，天庆就庆对。No, that's not correct. This is the language is English, so you should just the introduction of yourself is in Chinese. Everything else should be in English. But of course, the name you use Chinese or English. It's okay. It should be okay. And then it's 3 minutes.太远了，我念一下，就是庆学嘛，9120，我碰了再说。前进，不是，它是庄中，Yeah, that's you, right?
Yes. The opponent is.
Right, opponent representative. 庄啊。
This one, right?
This one, right? Yeah, right. That's right. 然后，双方的是，我刚才是争论，所以应该中文一看就知道了。
第二个。This one?
应该是曾子晴 ，correct？ 曾子晴。
Honorable judges and worthy opponents, I am a member of Team Palace, and today we're going to discuss question number 4, unsinkable disk. This is our outline. So I'll first introduce this problem statement, our focus, phenomenon, and setup, and then I'll move on to the theoretical model, and then I'll talk about our experiments and result, and what we realized to be the boundary conditions, and then I'll give the conclusion. So for introduction, as the first figure shows, the metal disk with the hole at its center sinks in the container filled with water. And as the second picture shows, when the vertical water jet hits the center of the disk from above vertically, the disk may float on the water surface. But however, when the water pump is shut down and the water jet stopped, the disk will sink immediately afterwards. So our focus in the following presentation I will first explain the phenomenon, and then I will investigate the relevant parameters, and finally I will determine its boundary conditions. So this is our experiment setup. We use a water pump to eject water from the tube, and a manual tube to direct it to vertical. And we have cut off various aluminum discs with different radius and mass. So before I move on to our experiments, I would like to introduce the theoretical model. So why could the metal disk float on the water surface? We believe that to answer this question, we have to separate it into 2 directions to discuss. So first, I'll talk about the vertical stable equilibrium. From the vertical directions, we believe that there are three main source of factors, which is the buoyancy from the disk itself, which will be directly affected by the air cylinder caused by water displacement caused by air cylinder. And the second and third are gravity impulses from the water stream. And then we move on to the horizontal stable equilibrium. So at first, when we were conducting the experiments, we didn't make a dent in the middle. So there's only just a single flat hole. And however, when the water is ejecting from the top, the disk may shift horizontally. And if it shifts to a certain distance from the middle, it will flip, or it will have a torque and flip over, and therefore it will sink. So in order to investigate this problem, we think that the disk also needs to flow not only just vertically, but also stably in horizontal direction. So in order to do that, we made a dent in the middle, as shown here. So when the disk shifts away from the middle, it will shift back. And this is the free body diagram that we draw to help us further on investigate the problem. So then I'll move on to the preliminary experiment stage. So at first, we want to eliminate surface tension because we already think that it's too small. And after a series of calculation, we found that the surface tension, the force given by surface tension is only 2.176 GW, while the total tower force, which is the combination of weight and impulses from the stream, is 20 times larger than it. So therefore, we think that since surface tension is too irrelevant, we will ignore it in the following experiments. And then we move on to discuss about the buoyant force. So in definition, buoyant force is the water displacement of an object. In this case, we could written it into the formula of buoyant force equals to rho, which is the density of water, times g, the gravitational acceleration, times a, the surface area, and times the air cylinder, the height of air cylinder, plus the thickness of the disk. However, after we measure the thickness of the disk, it is only 0.03 centimeters. So in this case, we think that it is too small, and we simply ignore it afterwards. So therefore, we fix this equations to buoyant force equals the density of water, rho, times the gravitational acceleration, g, times surface area, times a, times the height of air cylinder, h. And since we have varied radius of aluminum disk and cut several different disks with different surface area, we separated each models and calculated the result as shown here. This is the buoyant force from the disk with radius. And as we further move on to experiment, we actually realize that there will be a stimuli jumping of water outside around the disk. And after research, we know that it's hydraulic jump. And the h determined here is not the pinnacle, but it's actually the height that it will reaches, and the final height that it will reaches minus the initial height, as shown in there. And so hydraulic jump is defined as hydraulic jump is caused by the transfer from kinetic energy to gravitational potential energy. And after we researched about it, we found that it's actually directly affected by Fro's number, as shown here. So Fro's number, the square of Fro's number is defined as the inertial force over gravitational force. So as shown, it will be Fro's number will be the velocity of water on the surface over the root of gravitational acceleration times characteristic length. So characteristic length actually has several meanings in fluid mechanics, but in this case, it's simply the height of the water on the surface of the disk. And Fro's number will have an effect because if Fro's number is too small, there will be no hydraulic jump. And it will, so from 1.0 to 1.7, there are rarely any jumps, and energy dissipation is less than 5%. So we define our hydraulic jump as Fro's number that is larger than 1.7. So as this graph shows, from 1.7 to 2.5 is a weak jump. From 2.5 to 4.5 is a collating jump. From 4.5 to 9.0 is a steady jump. And when it reaches larger than 9.0, it will be a strong jump. And the energy dissipation will also increase significantly as the flow number becoming larger. So therefore, we actually realize that there is a boundary conditions in this case. And because Buoyant force equals to low times G times A times H, the H, which is the air cylinder caused by water displacement. So in it, as I have introduced hydraulic jump, this is also affected by hydraulic jumps. So because it's affected by hydraulic jumps, there will be a lower limit and a higher limit of the radius of the disk. As shown in here, the red line is the approximate maximum height that the hydraulic jump could reach, as the empirical formula suggested. So this is this segmented places is actually suggested by empirical formula from fluid mechanics that hydraulic jumps is actually segmented from due to different distance height. So therefore, we approximate the maximum height of hydraulic jump to this red line over here, and then we put it into this graph. And so the max height possible that hydraulic jump could reach is the red line over here. And since hydraulic jump will affect buoyancy, it will also affect the height required for the disk to float. As radius is becoming larger, the height required to float is actually becoming slower. And we found that the first intersection of this point is when the radius is 2.74 centimeters. The hydraulic there will be a hydraulic jump of 0.0146 meters, and this will be the first point that it could theoretically float. So from our calculation, we graphed out this line that shows the relationship between hydraulic jump and the max height required to float. However, because due to its water viscosity and the friction done by the surface of the metal, the Vs of the surface will actually decrease as it flows out of the center. And it is shown in this chart that the Vs decreases when distance away from this center is increasing, which means the radius is increasing. So it will continuously decrease. And therefore, when the distance is over 7.2 centimeters from the center, the flow number will be lower than 1.7, which means there is no hydraulic jump, so there is no height difference, and there is no buoyancy. So there is no buoyancy to support the disk. So we draw this graph that shows the relationship between flow number and distance away from this center. Therefore, we graph out that there's also a maximum height the maximum radius of the disk. So when flow number reaches when it reaches below 1.7, there will be no hydraulic jump force in the surrounding water of the disk. Therefore, there will be no air cylinder formed in the surrounding water, and thus buoyancy will fail to keep the vertical equilibrium of the unsinkable disk. And as shown in this graph, the blue line is the impulse force plus the weight of the disk, which means the total downward force. And the red line is the buoyancy force from the disk when radius is over 7.2 centimeters. As we suggested that if the radius of the disk is over 7.2 centimeters in radius, there will be no hydraulic jump formed. So, and as we have said before, we simply neglect the thickness of the disk. So we approximate that the buoyancy after that, when the radius of disk reaches more than 7.2, will be a constant which roughly equals to 53.6 GW. So in the end, while buoyant force already provided an adequate upward force that could hold the aluminum disk vertical equilibrium, we realized that it's hydraulic jump that actually determined its boundary condition for the disk to be unsinkable. And the dent in the center of the disk helped maintaining the horizontal equilibrium of the disk, thereby ensuring the vertical equilibrium by stabilizing a height difference of air cylinder caused by the hydraulic jump, as I have informed that before that. We think in order to keep the disk unsinkable, we also have to maintain its horizontal stable equilibrium so that it will not flip over. And this is our reference. And and thank you.
Okay, so my first question will be, what parameters did you use in your experiment?
So our parameters as we have various radius of the disk, and since the aluminum disk is mass produced by factory, we believe that its density will be the same. So
Okay,
mass
so can you define where the air cylinder you mentioned is?
So as shown in this graph, that hydraulic jump will cause a height difference, and the disk actually floats slightly below the water surface. So there will be so the disk of the water surface is lower than the surrounding water of the disk because of hydraulic jump. And we does not count this pinnacle because the hydraulic jump height defines.
Where is the air cylinder? Excuse me.
Right here. The orange part.
So in your observation video, can you point out where we can see hydraulic jump?
You mean I shown
yes, in any other video. Can you show
the introduction?
Yes.
So here, and as you can see, there is actually a higher part surrounding the disk.
Yes. I see something like a standing wave right there. So did you consider standing wave?
No, we don't think it will affect the system at all.
Okay. So how would you explain how your hydraulic jump? So you have water on your disk, right? So would the water on your disk have any effect to whether it will float or not?
Oh, you mean like the flowing water upon the disk?
Yes, yes.
We think the mass of it is negligible, so we didn't really count it into the total downward force.
Okay. And last question. Do you think water will go, like the jet will go under the water surface?
Time's up, should I answer or?
It's blocking my view.
Oh,
So that's it.
okay, thank you.
Question. takes the floor.
Okay.
Hopefully.
So, hello everyone. I'm Joe Zhang from team 9120, and I'll be the opponent for question number 4. Okay, so first of all, public statement of metal disk with a hole at the center sitting with a container filled with water. When the vertical water jet hits the center of the disk, it may flow on the water surface, explain this phenomenon, and investigate the relevant parameters. Okay, so the crucial points are that we believe it's water jet velocity, the mass of the disk, and the shape of the disk. Okay, so first, summary of the report. So the pros are that it does include very many pictures and a lot of graphs to show its theoretic model, which I think is very clear. And there is also many charts, and they did give a pretty detailed theory. However, some cons are that they lack pretty much parameters. So as I see, they only did they only changed the radius of the disk, and however, and when we talk about changing the radius of the disk, they actually didn't consider the mass of the disk, and and they didn't mention their experiment method, and they actually didn't mention what how their theory relates to their experiment. Okay, so points to be discussed. So first, phenomenon explanation. They mentioned the hydraulic jump, and we will be discussing about how to measure the boundary condition that causes it to flow or sink. And the theory, they mentioned buoyancy, gravity, impulse, hydraulic jump, and Frost number. And they also discussed about the horizontal force, which I think there is something to be discussed right there. And however, I think they're missing what happens under the surface of water, and we can talk about that later. And also the standing wave, which I think might be might affect how the whether it flow or sink. And next one, experiment method. So they are lacking pretty much experiment method. So we will be discussing about how we can improve that, and also their depth controlling. And next one, the parameters. So first of all, the mass of the disk, because they changed their radius, but I don't see in their theory how the mass of the disk will affect its theoretical value, and what it happens under the surface, and the depth of the water, whether it will affect this this phenomenon. Okay, so there are in a discussion, we will be focusing on how to connect their experiment to their theory, which I don't see a lot of connection in between, and I have a few questions about that. Their charts line too. Okay, I'll be moving on to my discussion.
Enter the discussion.
Yeah. So let's start with our boundary condition. So could you give a quick explanation about what boundary condition will cause it to sink?
So as I mentioned in the presentation, we have the factors that actually affects our boundary conditions are the hydraulic jump. So as I have already shown in the here, that hydraulic jump's height will actually affect the buoyancy. So therefore, when it's affecting the buoyancy, it will have some intersection point, and therefore we can get.
Okay, so just to make it clear, so you believe that buoyancy will cause that thing to float, and hydraulic jump will affect the buoyancy.
Yes.
So hydraulic jump will affect this phenomenon.
Yes.
Okay. So besides of hydraulic jump, did you consider anything else that will affect buoyancy?
So as you have mentioned in your presentation, you think I think you have misunderstood our chart here. So the height required to flow, we actually because the height requires it will affect the buoyancy, right? And
also, sorry, what height is it right here? The height of
the height requires to flow.
No, like what height? The height of water jet or the height of
the height of hydraulic jump.
The height
of water jet wouldn't really affect this part. It's only affecting the.
Okay, so the height of the water jet wouldn't.
Yeah.
So this is the height of a hydraulic jump.
Yeah, this is about the height of the hydraulic jump, and since height of hydraulic jump will affect the buoyancy, we chart out this chart. But in consideration, we also, as you have mentioned, that different masses may also be a consideration. We did consider it into this chart, because as I have shown in the previous one, that we believe the vertical stable equilibrium will be buoyancy and gravity and impulse from the stream, and gravity will and the mass will be affecting this. So,
could you tell me what will affect the height of the hydraulic jump? Because I think if you only consider the height of the hydraulic jump, and for example, not considering the height of the water jet or like the velocity of the water jet or the impulse that it creates, then you might want to give an explanation about why these things wouldn't affect your hydraulic jump.
As I showed here, this is actually according to our research, and you said that we didn't consider the height of the water jet. But in our experiment, the height of water will only affecting the velocity of the surface,
yes,
and this will affect the Frost number, and Frost number will affect the hydraulic jump's height.
Okay, so
this is get from empirical formulas from experiments, because
this is your theory, right? So
yes.
Can you show me where in your experiment I can see the energy dissipation? Sorry. Where can I see like because you gave numerical ranges, right? So I would like to see where you can demonstrate your energy dissipation. Would it be the height of the hydraulic jump, or perhaps how heavy the mass of the disc is, and or what the buoyancy is, or like where could you show that?
You mean the energy dissipation?
Yes, yes.
Because this is so hydraulic jump in definition will be caused by the transfers of kinetic energy of water jet impulses into gravitational potential energy when it hits.
I understand that.
Yeah, so this energy dissipation is only about that part. When it transfers kinetic energy, there will be some energy dissipation.
So because you mentioned Frost number, right? So just since you mentioned, so is there so in your experience, did you calculate Frost number?
Of course, we calculate Frost number. Because
where is it?
This is in the chart. Yeah.
Which one?
I think I will have to maybe explain this again. So
just show me where
this
the
is the
Frost
Frost numbers line.
Okay, so this is from the experiment, right? Is this theoretical, or is this from your experiment?
This is from the experiment.
And is that only one point, or is it a straight line?
No, this is not a straight line, and this is not one point. This point is just to mention that when Frost number are below 1.7, there will be no jump.
From your experiment, you got a Frost number that is linearly relevant to your distance away from the center. Or is that a curved line?
That's a curved line, but as I have mentioned, that the Frost number will be affected by the velocity, and if the distance from the center is longer, the velocity will become slower. It will decrease because of viscosity and some of the friction caused by the metal disc.
Okay, thank you. Then let's move on to your experiment. So, can you go back to your observation video, please? Observation video? Yes. Yes. Where you can see. Yes. So you said that I see from the second video there is hydraulic jump. So it's a wave, right?
It's not actually a wave.
I can see the ripple, right?
I mean, this is just because the water flows out and it bounces back, so there will be some seemingly wave, but it's not actually affecting the system at all. It's not a relevant factor.
So you believe that the wave bouncing off the wall would not affect?
It will not actually affect at all.
Yes, but my question here is because actually from your chart I can see that the hydraulic jump height is actually not quite. It's not like a 5 centimeters thing, right? It's a couple of millimeters. So, and the wave, I cannot see how high the wave is right here. But if the wave is a couple of millimeters, then it might even go above the disc. which will affect your hydraulic jump. Right?
It's just a water flow. It's not the weight. It's not. Yes. It's not really a relevant factor that would affect it. And our height of hydraulic jump is actually, according to our research, and I have already said, this is fluid mechanics. So a lot of things is actually come from empirical formulas. And I've also mentioned that there's a segmented part because this is from empirical formula. So this red line here, that is actually our approximation. Yes.
Yes. So how would you? So okay, let's get this because okay, seems that we can read each of this. And how would you define when like for example, I believe that so you turn on the water jet, right?
Yeah.
And then this will flow on the water. And then, like at some point, the water jet is not enough to create enough hydraulic jump to create enough buoyancy to that flow, so it will sink, right? So
yeah.
how did you measure this part?
You mean what? Which
Yeah.
part?
So how did you define when the disc will sink? Like yes.
The disc will sink when it's, as I have mentioned here, there is a upper limit, and this upper limit is also due to our previous.
So you got this from your experiment?
Yeah, we got this from our experiment.
Alright, so I seem I have one mistake here because I thought these were all theoretical because I didn't see any data.
Yeah,
for it.
so we have caught several discs, and this is actually done by experiments. Yeah, and several discs. We also have considered a lot of things from yours. Several discs, like we have the weight, we have the diameters, and we have the area.
Oh yeah, talking about weight and the diameter, you mentioned that once the diameter gets way bigger than what's the number again?
You mean the
yes, like how big it gets, and then it cannot flow. Right.
It will, if it's the diameter gets over roughly about 18 to 18.3 centimeters, it will fail to flow.
It will fail to flow. And did you was that theoretical or so? Did you fail to let it flow experimentally, or was that just a theoretical?
We actually cut up a lot of different plates, and this is not all the plates we have cut. Oh, sorry, we have got this 7 here. We have put it on, and this is 20. It says 20 here in diameters.
Yes.
And this one couldn't really flow.
Okay. So did you ever consider turning your water jet higher? Because I believe that if you did turn the water jet higher, or even if you let the container of the box, the container be longer horizontally, then why wouldn't it flow? Because
okay, I'll first answer the one with water jet height. Okay, so you have mentioned about water jet height, and actually it only affects the surface velocity, right? Because when you have higher water jet, the energy will transfer larger, and the velocity will become larger. And so mathematically, we can actually calculate, we can actually predict it by this formula about Frost number, and so we can actually know it from our mathematical.
It seems that if V here is bigger than the
so you have mentioned height. If height is higher, the V will be bigger.
Yes.
And so when V becomes bigger, the condition that we have given are going to be changed because the condition we given is that it's the same height. And about the one you mentioned about we have actually conducted experiments, but we realized that it doesn't really affect this.
So is there any effect under the surface of water? Because I believe that maybe the flow under the surface of water will actually give it an extra force.
I know. So I know your question, and from our experiment setup, we actually put an ink into it. I think this might be a confusion to you. So the ink right here, which shows the water flow, and there's no flow that actually comes out, bounces out back. So we don't think there is any flow of water. Okay, thank you.
Okay, so in our discussion, they believe that the only thing that will cause this phenomenon to happen is the hydraulic jump. But however, they negated. They believe that parameters such as the depth and what happens under the surface and the standing wave would not affect its phenomenon. And in our discussion, we also discussed about their experimental methods and how their experiment is related to their theory. However, they did not show enough evidence of their experiment, so that might be a lack of in their chart. Yes. Thank you.
Okay. Now we review it. Explore. Really.
Can you explain the phenomena of this float on the water surface? And you mean that the disk can float on the water surface, it all depends on the hydraulic jump, or you consider about the vertex under the water surface?
What do you mean, like consider the vertex on the water surface?
What do you think about the water jet when it hits the center of the disk, and the water will have a vertex?
Oh, so that's the same question as the opponent have asked about the depth. And we have done experiments with different depth, and we have the one that is actually that high, roughly that high. And within that system, the result of our experiment is actually the same. Yes.
And so you consider about the limit of the disk. Do you use the flow number to calculate this?
Yes. It's we depended the boundary condition from our calculation of flow
And
number.
do you do a variable of the water jet velocity?
We don't think there's a need to do that because it's just shown like it's directly proportional to.
Do you think the water jet velocity will influence the limits of the disk?
Yes, I do believe, because as even as in this horizontal number of the water velocity is inside the equation, and besides that, if the water jet is greater, then we can say that the impulse it gives to the disk will even be bigger, and that might cause it to sink or have extra, for example, is high jump.
When the water jet velocity is bigger, and the disk will very specific that it can float on water surface.
Are you asking me that if the water jet gets bigger, will it float easier?
Yes.
Yes, I believe so. Yes.
And do you think there is a relationship between the water jet velocity and the height of hydraulic jump?
Yes. So the water jet velocity and the height. So the height, of course, because of the potential energy to your kinetic energy, it will affect the water velocity. However, their pump, like their experimental pump that pumps water, gives it an initial velocity, and that will also affect the water jet velocity.
What about the flow number? So you calculate when the flow number is smaller than 1, and you will have a limit.
1.7, there will be no
1.
hurdle. Yes. Yeah, we think that.
So your experiment is about 1.7, because the theoretical one is 1 meter.
Oh, so as you said, I know what you mean, like about this part, right? Like there's actually an A chart, right? But in here it's a under jump, so it's actually really any difference. So
your hydraulic jump you think is supercritical or in subcritical?
3 minutes.
Thank you.
Okay. Okay, the review page before.
Hello everyone, and today's review is on High. And for the public statement, it said that the middle disk puts a hole in its center sink in the container filled with water. And when the water jet hits the center of the disk, it may flow to the water surface and explain the phenomena. An overview of the reporter. An observation is an air glider and a theoretical model. And the parameter experiment and the beyond force. And the theory is for the binary slow and the hydraulic jump. And the variable is hydraulic jump and boundary condition. And the velocity and the flow number is resistance. And the cause is an important part of a reporter's PPT. And the cause is too much word on the PowerPoint. And they don't use and it's lack of the experiment. And overview the reporter. Overview the opponent. The speed is water jet of the velocity and the mass of the disk and the density. And the density is the same. So we can see there is a very clear experiment result of the mass and the radius. And for discussion part, the topic is vector about phenomena. And reporter's opinion is and the opponent's opinion is the wave bouncing back to a disk. And the reporter said it won't affect a lot. And I also think it won't affect a lot. And the factor about the hydraulic jump. And reporter said that the hydraulic jump is the main for the hydraulic jump is the main character that like the disk can float on the water surface. And for the basic points, the reporter considered about the water jet velocity, but he didn't find out the limits of the disk can flow, and also didn't consider about the water jet velocity. And for the suggestion, the reporter may put more experiment to explain it more clearly and thoroughly. And the opponent may can add something like the vectors will reaction together, and they also can consider about the water jet velocity, because I think water jet velocity is very important in the flow number. Thank you for your attention.
Good. You report. You have 2 minutes. It's done. Report. Report. Okay.
Okay, so for in the end, we would like to conclude our discussion with the opponent. So this is the problem statement and our focus. And so for some clarifications, we would like to say, the curved line of the upper limit has already taken mass of the disk into consideration. So we already put it into our chart. And the mass is since the mass is directly proportional to square of the radius, the mass is directly proportional to the square of the radius since the thickness of the disk is the same. And the second point is that the height of the large ring only affects the surface velocity. And since our theory is based on Probst number, our theory can work for all velocity because Probst number kind of really is just equals velocity. And thus we do not have to conduct experiments on other velocities. And in the end, there is no standing wave in the system. The ripple-like waves are the reflection of water flow of the container walls. And furthermore, it will not affect the hydraulic jump because it's very stable according to our reference. And the opponent has misunderstood our chart and asked some irrelevant questions. And the opponent discussed about the parameters that have already been taken into consideration and during calculations and experiments. And finally, the opponent was not able to recognize the various parameters in our experiment. Thank you.
Good.
Okay, that's only. Sure, okay, now I'll ask some brief questions. Anyone has any comments or questions?
I have a question for all of you, because we are discussing about hydraulic jump during your discussion. So I'm thinking that if we carry out the experiment on the moon, what would happen on the moon?
As I have shown in the first numbers equation, on the moon, the number of G will be different. So so if the G is under the equation, G is under the V velocity. So if the G is only 16% on the Earth, we believe that it would be only 0.04, like about 0.4. So it will be larger. The force number will increase, and therefore hydraulic jump can jump higher. And when it jumps higher, it could have like more heavy load. So yeah, thank you.
Okay, so because the G will be smaller, right? And so will the mass. So will mg. The weight of the disk. Sorry. The weight of the disk will be smaller, and because G will also be smaller, so the buoyancy will be smaller. So everything together affected by the gravity will all be smaller. So I believe that there wouldn't be any changes in the hydraulic jump.
And the gravitational number, it will be smaller, and the atmosphere on the moon is also different. So I think the force that makes the water go down is smaller. And if we would like to use hydraulic jump, maybe the water jet velocity is bigger, and it's more easier that the disk can float.
Another question? No? Talking about the hydraulic jump, is this on the surface or it is in the vertical direction? Why you keep saying hydraulic jump? Usually, talking about hydraulic jump, we talk it on the surface, right?
Yeah, and it's
higher, and so the pressure
yes.
under the disk, the difference will be larger. The buoyant force will be greater, right?
Yes.
So your hydraulic jump is on the surface
Yeah, it's a phenomenon.
because it's higher, and then so
it provides a greater distance
buoyant
difference.
force.
Yeah, because it provides different.
So the other two, what do you think?
Okay.
Where the hydraulic jump located?
So the hydraulic jump is going to the surface, right? So there will be
Surface under the disk, or
for the hydraulic jump, it's going to the surface, and there will be a difference in pressure, and then which will cause it to float. Yes.
For hydraulic jump, we think it is on the water surface, and the water surface it has a thin flow, and the velocity of there it can through the shear force to consider the velocity. So on the most surface, and the velocity is the most bigger one. And for under the disk, and actually the vortex will make the water to the bottom of the container. So that's it. Thank you.
yes. So you mentioned about the Bernoulli effect. and the vortex, right, under the disk. You seem to be pointing out that they should be considered.
I think that should be considered.
Go ahead and answer the question. So we're thinking that because
And it should have to be quick.
okay, sorry. So we're thinking that Bernoulli force and definition should be act on the same timeline. So we don't think Bernoulli should be considered into this vertical.
Why not? The water jet comes down and then wait.
But we have also but we have also done we have also done experiments with larger depth, and so the water flow rate actually comes out with the effect flow is actually very slightly. So with very
slightly because just under this, right?
yeah, but
Okay. Yeah, I got your point. Yeah.
Yes, so I believe things under the water should
Okay. Should be considered.
yes, it should be considered.
Thank you. Okay. Now let's have some time for the juror to evaluate the performance. The others probably are ready. I'm not. Okay. Let me check see if others. I guess you are already. Okay, so we will show the scores starting from right 676 for the. This is for reporters, right? Everybody understand? Okay, 6, 7, 5, 6, 6. Okay. Now for the opponent. Ready? 7, 7, 6, 6, 7. And then the reviewer. 6, 6, 5, 5, 7. Okay. So that concludes this stage of fight. Thank you.
Thank you.
If any question, but make use of the break. Okay. We will take 10 minutes, 5 minutes, 5 minutes, okay. 10 minutes, okay, 10 minutes break. So 5, 10, 5, 40. Should be 10 minutes. 40.他的力的一个他没有
而且它的记的话，它是最高最低的价格没有，我看最低给的第一没有举。那他说如果是 H1，那你要算出它的交互感，因为 H1它的 COD 它是说它的 fast number A， 所以基本上但它没有然后它的跟那个有一条线，所以你要清楚了，你在学习的人你要是接受，可以做 business， 那看，好，等一下再仔细一点看看下去，所以大概然后 summary 应该要不然他一开始5分钟的，然后功能基本上理论上我们在做的时候是其他，因为其他人其实没有所以你们应该要列说为什么要问第一个问题是什么？那我们就是比如说他1分然后接下来我们讨论，然后我们觉得这样子他会比较知道，不然他一开始大概有前20秒就是然后发展看对，detail， 然后就是你可以就直接讲出他用的什么
10分钟的话，你们都知道要换队哈。
他换
位置要换，是不是？对啊。那个位置是要换，
验收一下。然后像他那个 info 到后来也不见了，就是后来也都没有好。这你应该说你可以秀里面告诉我，他说这个 radius 太大，应该是哪个不等式去判断它。因为你还说很多，还有条件是怎么样？然后你的 radius， 你应该是讲他改 radius 再改 max， 这样。但我觉得你讲的都很具体，就是我有点听不太懂你的 radius 想要讲，应该是想要讲他改 radius 是改 max， 可是他的波浪形应该也会改，因为他面积在改，所以你应该要讲，就有点不够清楚。我大概知道你想要讲的，对。先移过去吧，哦，不是，先移过去，另外有没有东西？我先看一下。
现在移啊。好，你去，我帮你看。这是比较我们好，对是吗？是。这个是雷射。哦，对，那就不用了。这个是我们。
刚刚是你们review的 point， 这个laser point 不行，是不是？是不是？可以呀。哦，他这有给你们，那个是要讲回来。
我来说这个。
这个书包是这个太多了。这个什么？完全是你的吧？
这不是我，不是我，这应该是，都是谁？这应该是我的吧？
我的电脑啊。你们可以先收完东西再去上厕所。
这个是。
对不起，对不起。我的铅笔了。那你都拿过去。
这你有什么？
这是什么？看东西。
这里的吗？
如果我那个简报太看不到的话，我可以就是说我们先走过去那边看，因为就是字太小看不到。
我也看不到。
所以我可以，
我是要站起来看，
就可以走过去。
你说你现在要在哪个位置？
没有，就是说之后的看法比赛，就是目标往边缘扫，然后看不到脸。
可以啊，没有说规定视力一定要多少。不要影响那个人贴心就好。听清楚最重要。Okay. For this stage, key for recorder is 9120. Then reviewer, right on the. No, you don't have to because you haven't chosen problem. The opponent, please challenge the reporter. Problem.
And we're going to challenge the opponent, ring on the right.
Number 1.
Question number 3, ring on the right.
Ring on the rock. Okay. Number 3. Now I decide to ring on the rock.
把3个剪刀开起来，好像我看这上面是3。
对啊，我以前买一些比较大的。对，不是，但是它另外P1 基本是电脑另外一个程序，这是它是这个。Excuse me, but to, if possible, write down Chinese characters so that our assistant can recognize who's representing. This would be still Zhuang. Zhuang? Yeah, 刚刚 Next time, there's no Zhuang. So same.
We will accept the challenge.
Oh, you haven't accepted it? I'm sorry. Okay. Because you already got it, so you must accept it. Reviewer, who will you be the representative of the team?那2个刚刚也都有，所以就是这个名字刚刚中文应该没问题。林巨轩。
my report. Okay, so I'm Joey Chong from team 9120, and I'll be the reporter of question number 3, green on the rod. So this is my outline, and we will start with a pilot statement, observation video, and we'll go through our theory and experiment and end with our conclusion. So pilot statement: a washer on a vertical steel rod may start spinning instead of simply sliding down. Study the motion of the washer and investigate what determines the terminal velocity. So here, first we will study the motion of the washer. We will categorize the motion of the washer, and then we will calculate the terminal velocity and then see what affects the terminal velocity. Okay, so observation. Sorry. Okay, so this is our experimental and observational setup. And so we have two cameras. One is above the rod, and it will be tracking the angular velocity of our experiment. And this one is a camera from the horizontal view, and it will be tracking our linear velocity of the ring or the washer. Okay. And this one, so in our observation video, you can see, so there will be a first mode, a rebounding mode, and a terminal mode. So basically, the first mode, I know you cannot see the video right now, we have some technical issues, but the first mode is the angular velocity would start to decrease after we give it a initial angular velocity, and the rebounding mode is the angular velocity would start to increase, and the terminal mode is the angular velocity would reach a the terminal angular velocity would it will reach a terminal angular velocity. And in the first mode, the linear speed would start to increase, and the rebounding mode, the linear speed will start to decrease, and again in the terminal mode, it will reach the terminal linear speed. Okay, so our definition for the ring or the washer, I would just call it a ring. M is the mass, and R is the inner radius, R2 is the outer radius, and E is the thickness, which we will use later on in the calculation. And theta is the tilted angle to the horizontal line. Okay, so there's 3 modes. And this is y dot to t chart, and which means that this is a linear velocity to time chart. So the prepared mode means that so when I give it an initial velocity, it will stay at the same height and spin, and so it will not have a linear velocity. But however, as the energy goes away, the angular velocity will start to decrease, and it will start to go down, and the linear velocity will come up, and in the rebounding mode, the linear velocity would come down as the angular velocity increases and reach a terminal linear and angular velocity. Okay, so this is just to show that it reaches a linear velocity. So this is extracted from our experiment. So this is our 4th experiment with different different washer or different ring and the same iron rod, and we can see that it all reaches a terminal linear velocity. Okay, so let's move on into our theory. So the different motions, we can categorize different motion by a different angular velocity. So there will be 3 different motions, and let's define. So here, this is the rod, and this is the ring, and this is the center of the ring. And we call psi dot the precession angular velocity, and gamma dot the rotation angular velocity of the ring, and R is the ring's inner radius, and small r is the rod's radius. Okay. So let's talk about our first mode. So there's three modes beside the preparing mode. So the first mode, this equation right here, to the left top, is considered out of Coulomb's law of direct friction, where C is the rolling resistance coefficient. So the first one, Ft equals C times Fn is the first equation on the gamma surface. So Ft will be Ft and Fz will both be the driving friction force, and the second equation with the Fz is on the horizontal, which is a z component. And here we can know that the normal reaction will oppose to the centrifugal force. So we can get this one. So Fn will be n times the rotating radius and the gamma dot squared. And drive friction force will depend on the angular velocity, because we have angular velocity here, and the drive friction is not related to Fn. So using Newton's second law, we can set this condition. So first, in the z direction, if gamma dot is greater than gamma dot zip, which is this boundary condition, it will be in the first mode. So once it gets lower than the gamma dot zip, it will move on to the next mode. And this is just an equilibrium of gravity and its friction force. And for the gamma direction, we can get this equation from the previous equation by substituting into that equation, and we can solve gamma dot of t to this answer, which we will talk about later. Okay, so for our prediction, because the z direction, as I mentioned, so this is the first mode. So once gamma is lower than gamma dot zip, this will not be the first mode. So we can only predict this line right here, and we use it by using this formula. Yes. Okay. So the first mode fits the theory, and we calculate that c is 0.0148, and this one is angular velocity to time graph, and you can see that in the preferred mode, the angular velocity is the same, and the decreasing mode, which is actually the first mode. I'm sorry to confuse you guys. The first mode here the angular velocity would decrease, and the rebounding mode is the second mode, and the terminal mode is the third mode, which it will reach a terminal velocity. Okay, so the second mode is, let's go back. The second mode is where it starts stepping, and the angular velocity would rebound and go up because of friction, and so that's, and we will not do experiments on that particular range. And so for the third, and which is the terminal mode, which is what the what the question stated. So the washer will reach a terminal velocity, and when gamma dot is constant. Okay. So here we will calculate the moment of inertia of the ring, and so by using the formula of angular momentum and the inertia matrix, and so here I1 is going through this line, and I2 is going through this line, and I3 is a line where it rotates, like just usually rotates. So I1 and I2 is symmetrically the same. So I1 is equal to I2, and I3 is calculated right here, and we have the angular velocity vector like this, and so which gives us angular velocity, which can be shown in this equation derived from the previous equations. So the third terminal mode, this equation is just using the same equation from as a free fall, and we just cancel out the mass and the radius, and so we can get that this alpha g is related to the z component of the affected by the gravitational force, and this c gamma dot squared is affected by the ring, the rotation of the ring. And so the potential energy would from the top, and of course the initial kinetic energy will change into linear kinetic energy and rotational kinetic energy. And linear and angular velocity would increase, which cause the drive friction to increase, and which will cause it to reach a linear and angular terminal velocity, which happens at the same time. Okay. So this one is a helical path of the contact point. And so our hypothesis is that there are no vertical sliding, so z dot is fully determined by the terminal angular velocity. So this is the slope of the helical path, and when we substitute into this one, we can get this equation. And so this one is our experimental data, and that is gamma theoretical, and this is gamma terminal velocity. And theoretically, it will be the same. So so we fit the curve line y equals x, and the error value is 0.06. Okay, so our conclusion: the original motion with the secure characteristics. So understanding the translation of sliding and spinning motion, and we gave qualitative explanation and qualitative model for the steady state, and which is the terminal and which is the terminal linear and angular velocity. And thank you.
Do you use only one rod to do the whole experiment?
Yes, we fix the same rod.
And what's your parameters for experiment?
We use different rings. Yes, we use
You mean that the different radius or different weight?
different radius.
And when you use different rates, so you will have different moments of inertia.
Yes.
How about the angular velocity? You mean you give it an initial angular velocity, but the initial angular velocity is always the same?
We try to make it pretty much the same. Yes.
And what's the height of your dip of your drop?
About 175 centimeters.
So do you ignore the air friction? Air resistance?
Yes.
Why?
Because we believe that because of its material, it's iron, and we believe that friction will cause a greater impact than the drag force.
And do you have any formula to say about the terminal velocity will related to some parameters?
So let me see. So the formula of our terminal velocity is is right here, and it will be related to the radius. Yes, and yeah, it will be related to.
So you mean that the radius is bigger, and how will it influence the terminal?
So if the radius of the ring, so if the radius of the rod stays the same, and the radius of the ring gets bigger, then the terminal angular velocity would decrease, and the terminal linear velocity will increase.
And why don't you measure the initial angular velocity?
We did, but it wasn't in our so we did have a prepared mode where we measured the initial angular velocity.
And hello everyone. I'm today's opponent. The topic is ring and rod. And the purpose statement is that a washer on a vertical steel rod may start spinning instead of simply sliding down. Study the motion of a washer and investigate what determines the terminal velocity. And the main focus is the motion of a washer equals the terminal velocity. And overview the reporter, the first mode, rubber mode, and the terminal velocity. And definition of the velocity. It has three modes: repair motion, first mode, and reverse modes, and terminal velocity. And for theory part, it uses Coulomb's law and drag friction. And also have many equations. And Newton's second law. And the conclusion is a wave interval. And the plot is fluent English and career diagram. We show many diagrams, for example, the angular velocity diagram, and also the terminal velocity. And explain the theory very clear, and lack of a variable to experiment. Didn't use the theory to explain this experiment, and lack of experiment, and also parameters. And the discussion. I would like to discuss the angular momentum to a reporter, and also the momentum of inertia, and the motion of the center, the center mass of the washer. And also, I will discuss about the terminal velocity, and I will find more parameters to discuss with the reporter, and also the recursion. Oh, now I'm going to a discussion part.
Okay, you reporter? Okay.
Do you have any experiment data to show?
Yes. This one is our experiment data. So this one is our theoretical value and versus our terminal velocity. This is one of them. This is from where we use a tracker.
And do you have you do the omega t diagram?
Oh, omega t diagram? Yes. Let me see. Here. This one.
So when the terminal mode, you have determined the terminal angular velocity. What's the difference? The terminal angular velocity, so it's stable one.
Yes, it's stable. So as you can see, the angular velocity here reaches a stable value. Yes. So we define this by as terminal.
And do you have any force diagram?
Force diagram? Yes. Okay. So this one.
It's only for the friction force.
So it's affected by gravitational force and friction force, right?
And what about normal force?
So normal force will affect friction force. Yes. So but it's mainly so if you give it a normal force, it wouldn't affect it in the z component, right? It's about that normal force that affects the friction, which causes it to affect it on the z component.
And do you consider about the centrifugal force?
Yes. Here, the normal reaction will oppose to the centrifugal force. This is why we have the normal force equation.
So the centrifugal force is all depends by the normal force.
It opposes to the, because it is in a force equilibrium on the horizontal. So like the ring doesn't go. So the ring doesn't go out of the rod. So and the rod is stable. So the normal force is equal to the centrifugal force. Yes.
moment of inertia will influence the experiment result?
So the moment of inertia, so here it would affect, because look, so the angular moment equals I omega, right? So if the moment of inertia is, say, it's bigger, then of course it will be, so let's start with the initial condition. It will be harder to turn, but if they have the same initial velocity, then it will have a larger moment of, it will have a larger inertia, and which will cause the drive friction effect on it to decrease, or say cause the change of the like timing of where it becomes the different modes.
So you mean when the water is more oblique, ink will have a bigger angle inertia?
I'm sorry, can you repeat that?
When the water is oblique, the oblique angle is a stable one.
You mean if it is tilted? So during this motion, let's go back to our observation video. Okay? Do it here. Let's go to the observation video. So this is all tilted, and this is not stable. And starting from here, it's stable because it reaches a angular and linear terminal velocity.
And what will the pilot angle change? Is it the smaller one in the terminal mode?
You mean the tilted one? So go to the last page where we have the. Go to the last page. Where we have that helical path. So the helical path. Yes, this one. So here is the linear terminal velocity, right? And this is the terminal angular velocity. And so as you can see, the angle would affect here by sine theta. However, there is a maximum angle because the ring cannot fully turn on the rod. So I believe that if theta increases, then of course the sine theta would increase like from 0 to 9 degrees, right? And so the linear it depends on the linear velocity and the terminal angular velocity. So the theta will have an effect on both of them.
And so you think the moment of inertia is the most stable character to influence the terminal velocity?
I think it's the moment of inertia because using different rings, we can both at least from our experiment, we can all observe this phenomenon. So I believe that the moment of because the rings are changing, right? So the moment of inertia doesn't limit this phenomenon to happen. And however, when we use our different rings, we do have different timings where we do have different gamma dot to t graph and y dot to t graph. So if you say it's the most important, I believe it's just because our force diagram shows that how do you say that? Just leave it right there. Yes.
I think your parameter is doesn't too much, so the initial angular velocity I think is not bigger influence.
So what parameters do you suggest that I should add?
Maybe you can try different rods to do experiments.
So different rods. So do you mean different rod radius or different rod
Loopings of a rod.
material?
Yes.
Yes, also different material. So
or you can make it a thicker one.
thicker one also. So changing the radius of the rod. All right. That yes, that seems to be reasonable because by changing the by changing the material of the rod, we can change the C coefficient. So yes, that would affect the velocity of it, and the changing the small r, which is the round of the radius of a rod, will also affect it. So I think that's the point.
What's the motion of the center mass of the water?
Center, as I mentioned, it's a precession. Yes. As you can see, yes. So the center of the washer would have a precession angular velocity.
So it's doing the revolution and the spin.
It happens at the same time. Yeah, so it's like
So the water
it's
will spin around the center of the mass, and the center of the mass will rotate around the rod.
the washer will yes, the washer will rotate around the center of mass. This is a rotational angular velocity, and the center of mass will also rotate around the center of the rod, so that is the precession angular velocity.
Just find any for percentage angular velocity and rotation of angular velocity.
Any related things? I think. Well, not that we didn't actually derive this equation that we didn't derive the relevance of between the two.
So you only know the angular velocity that the ring spin.
Yes.
So you
Yes.
didn't measure the center of the mass spin.
Yes, because the problem statement. So the problem statement, it would, yes. So we only for this terminal velocity only discuss the angular velocity and the linear velocity. Yes, that's the only two we could discuss. But I would, yes, but I will agree that if we can track our precessional angular velocity, then we can. But I believe that it will still have a terminal velocity. Yes.
And why don't you try to use angular momentum?
Angular momentum? Yes, there is. This at the yes here. L equals I omega. Here we did consider the angular momentum.
The angular momentum is related to the angular velocity.
We can phrase it this way. So because the inertia is constant here, right? So we fix up the moment of inertia. So the bigger angular momentum that is act on it, it will cause a greater angular velocity. So this is what this equation means. Yes. Yeah.
Do you consider about the center of mass, the angular momentum? The precession angular momentum.
Precession angular momentum?
The center of mass, it have an angular velocity. And
Yes.
what about the angular momentum for the center of mass?
We don't think we need to consider that because it's or could you tell me why you think we should consider that?
For my opinion, I think the sentiment of the water's angular momentum will rotate around the rod.
Yeah, so what's the difference between, so I consider this, right? So there's inertia at this axis, and this axis. So then I just include the center of because you have the center of mass because you have this ring, right? So I consider the ring. So doesn't that mean that I consider the center of mass? Because you wouldn't have the center of mass if I didn't consider the ring, right?
Okay. 1 minute. Summary.
And for summarize, we discussed about what determines the collision velocity, and we find the moment of inertia is bigger, and it will have an angular velocity, and it will cause a different mode. And the second point is what the angle is not vertical, and the angle is minor. And there will be a maximum angle of the water rolling down. And we also discussed about moments of inertia, and different rings, it have different moments of inertia, and they were related to his equation. And we also discussed about center mass motion. And the reporter said the equation can show the reasons. We think that the reporter can do more experiments because he didn't have many parameters. And we suggest the reporter can comparison the experiment and theory to see there is still some factors that we can think about, for example, the rod. Thank you.
So, for a reporter, can I go back to your experimental setup?
Yes. Okay.
So, I've seen that the upper part of the green rod was not fixed. So, I think it might have caused a vibration on the rod.
When we did that experiment, we did fix the rod. Yeah, so we fixed it by our hand, and during the video,
Can you go to the page that have the linear velocity?
Next page. Yeah. Previous page. Previous page. Yes, this one.
Can you define what does the y-axis mean?
So it's the linear velocity. So like when the ring goes down. So this is y dot.
Y dot means
the linear velocity.
the vertical
yes,
axis.
so, yes.
But in your presentation later,
Yes.
I've seen that all of your vertical axes have been z dots or z.
That's
So-
our mistake. Y dot is the same thing as z dot.
So for the poster, you brought out the discussion about lack of parameters. So what else? What kind of parameters do you suggest them to add to their experiments?
Maybe we can control radius and change different the weight, and also the material of the rod and the height of the rod.
Okay, thank you. And the poster also brought out the air resistance. So may I ask you why the air resistance can affect the system?
Because I think his rod is long enough to resist air. Maybe it will. Or maybe.
Okay, thank you. Can you go to page 18? Yeah, so for the first one, the z dot equals omega over 2 pi. Does that mean that you assume that there's no sliding?
Yes, because in this terminal mode, the angular velocity is greater than, as I mentioned in the previous pages, it's greater than, we have this bounding condition right here. This one? Yes, so it's greater than gamma dot split. So because yes.
But how do you define gamma dot split?
We use this to calculate.
Okay, but how about the poster? Do you think it's always stay with a contact point or 2 contact point, or maybe there's the sliding?
I think that is.
Yes, there is less sliding during our second motion, but the first and third motion there is sliding.
왔다. 얘들아.
So I'm the reviewer of the question 3 in on the rod. So as the problem stated, we think the focus should be on the motion of the washer and also the terminal velocity. So the report discussed about the phenomenon of the washer on the rod, which is the linear velocity and angular velocity. And also they separated the whole motion into 3 rods, which is clear analysis. And it shows that the linear velocity increased and then decreased and then reached its terminal velocity. However, the angular velocity actually decreased and then increased and then reaches the terminal velocity. So for their theory, they have taken Columbus' law and law of dry friction and also the Newton's second law into consideration. And in a rebounding mode, the angular velocity rebound because of friction. And also, in terminal law, the moment of inertia and angular momentum has played a role into determining the terminal velocity. For the pros of the reporter, they observe the phenomenon from various angles, which can demonstrate that the rod has reached the terminal velocity. And also, they have a clear flow chart for the analyzation of the potential energy, and has a low error value of 0.6. However, they failed to show a video for how a whole phenomenon, and also failed to explain the source of the error. And they kind of lack a concrete evidence to show how their theory could be correct. And also they lack of conclusive remarks that show what parameters actually determine the terminal velocity. And also they did not test a different rod, which is a lack of parameters, and they failed to measure velocity of the center of mass. And for the opponent, they suggest a different parameters and also consider tilting in the experiment. However, they have some confusion questions for reporters, and for the first discussion, they have discussed about terminal velocity. And our opinion is that there is a certain variation on the chart, but without calculation and experiment to prove it. And also the second discussion is about their normal force and centripetal force, and we believe that the normal force should be equal to the centripetal force in order to reach a terminal velocity. And they also discuss how will the moment of inertia influence the experimental results. And we think that this question is irrelevant because the formula has already taken this into consideration. And they also suggest to try a different material of the rod, which I agree with the opposer that it should be irrelevant parameters. And then the opponent asked how did they measure the velocity of the center of mass. However, the reporter answered no, they did not. But I think this is paradoxical because then how did they plot in the chart of the terminal linear velocity? And the opponent asked it.
You sure?
And I think that the reporter should consider the moment of the center of mass, but they did not consider rebounding mode.
Report.
Okay, so I'll give some concluding remarks. So this is what the opponent said, and this is what the reviewer said. So first, let's start with the opponent. And so they asked about our theory, but I believe that I did give a pretty detailed explanation, and they thought that our parameter isn't many enough, and they gave the suggestion that we can change the radius of the rod and the material of the rod, which we both agree. And they repeat angular momentum many times, but they ignored the angular momentum is proportional to the angular velocity. And they thought that the air resistance would affect, but we think that the effect is very small and it's negligible because we only consider friction here, but they didn't give evidence where how air resistance would affect it too. Okay. So the reviewer, they believe our parameters need to be added. Again, we agree with that, and they thought that our data doesn't fit our theory. But I think that our error value is 0.06, so it's very accurate. And they think that we don't measure the center of mass, but yes, we measure the center of mass, as I said, from the to determine the linear velocity. Yes. And so. Yes. Yeah, this is a type of hair. We think that the effect will be very fun. Okay, so after our discussion, some things this report could improve on is its parameters, and maybe we can show some more videos to give evidence that motion actually occurs rather than just giving some mathematical graphs. Thank you.
Now, question for the jury.
Yeah, so maybe for three of you. So during the discussion, you guys mentioned about its worth to try different material for rock, rock of different material. So could you comment, try to guess what's the difference of motion if you use high resistance or high friction and low friction?
Okay, so I guess that because the rod will change its drag coefficient C, right? To change its coefficient C, and I believe that if the resistance is higher, then the first mode or the second mode would be very small, will be very little, or even don't exist, and it will reach the third mode pretty quickly. Yes.
And we believe that if the rod has a lower resistance factor, the rod will be sliding more, which needs a higher angular velocity to keep it on rolling without slipping.
And I think a different material have a different friction force, and the friction force can resist the weight of a washer, and it will reach the terminal velocity earlier.
Okay. Last question. Okay. Is this a rigid body problem? Rigid body. That is, everything's rigid. No deformation.
I'm sorry?
Rigid body. You have deformable body. You have rigid body. Now the question I'm driving is that your equation of motion should reflect that of the rigid body, right? Yes?
We believe not, because the vibration.
It is not what?
Because the vibration of the rod.
That's a
yeah.
vibration of the rod.
Yeah.
But it didn't take account of that at all.
So sorry.
The reporter didn't take into account of vibration of the rod.
But
you say washer or
the question was that, do you think this question, like the whole system?
that is the washer is a rigid body, right?
Yes. Yeah, Roger.
So shouldn't this really be a problem of rigid body motion? Yeah, right. How about you?
For rigid body, and I think we would like to consider the two motion. The first one is the center mass of the washer, and the other one is the washer.
That's okay. Rigid body, you just usually you separate into center mass motion and the rotation about the center mass. That's precisely what you did, right?
Yes.
But you didn't write out the equation at all. Now, I have to say, this is from the reference, the University of Paris presentation. You should mention it. Okay? You should show the at least, because
Okay, yes.
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 I have a question related to the question that I think at the moment you haven't already answered the question that because both of you didn't answer the terminal speed will change or not. If we use like the material is less friction.
So I believe that if we use a material with less friction, so as he said, the angular velocity, initial angular velocity has to be greater for some motions to happen, and during the terminal mode, we can the friction force provided will be less because the friction coefficient is much smaller. So I believe that it would, first of all, if not, it will be harder to reach the terminal velocity. Then the terminal velocity would be greater linearly and smaller angularly. Yes.
But for a lower resistance material, the maximum tilting angle to reach a terminal velocity will be less, like horizontally less. So that the rolling should be faster. Yeah, the vertical terminal velocity will be lower. But for the rod to maintain the tilt angle, it should be rolling faster. However, it will cause it more easier to just slide down the rod, but not rolling.
And if we use a bigger friction, if we give you a bigger friction, and the terminal velocity will be the smaller.
okay, that's all. Thank you. We'll show the score. Okay. We are all ready to show the results. Good, please, for the report. 6, 8, 6, 8, 7. Average 7. Now for the opponent. 6, 6, 6, 5, 6. Okay. Finally, for the reviewer. 6, 8, 6, 8, 7. All right, that's all for this stage. Thank you. Okay, 15 minutes.
I will remember to my preference.
You should. I recognize almost everything there. 番茄的一个角动量等于 I 乘欧米伽，角动量是向量，欧米伽是向量，那个 I 是一个张量，这只是角动量，你还没有写出转动运动方程式，就是你角动量的10变一要等于这个 I 阿法。那原来那个巴黎那个他也没讲这个，说这个应该是标准的当体运动的分子，这个他不会跟你太多讲。大学的话，这个他可能找回这个写出来就是微软的 equation。所以嘛，那，他执行的我没搞。对，执行就是沿着，因为你已经讲了，角度不变，它根本是离那个中间，它就是垂直的。直行的运动是一个线性运动，是一个沿直线的运动。它那个就是由垂直方向摩擦力重力正确，这个都知道。重心的运动是外力，那你外力垂直方向，现在就是这个摩擦力相冲，还有重力，就是这样。所以这个因为太标准，所以我们刚才可能大学的时候不会去讲这一件事情，但是其实这个就一定是这样。然后通常要接的论文一定是接着你只要谈要实心怎么找到，所以我们接着这个其实就是那有一个回来油拉就这个最多就几个字会可以解出来，但是巴黎这个还没有把你写出来，还是给答案，这个是找答案。谢谢。OK。
这个钢铁工程会解释。第一场的话就是计算在从哪来？那第二场的功能啊，最主要的方式是你在问问
整个 discussion 的过程分析出来，所以我会感觉到这个不断的比较相对有问题，没有说积极的同意，所以我觉得建议说的是，在 discussion 的时候，可以先说出你的观点，为什么这个问题超重要？会比较凸显出一个自己的问题，最主要是这一点的因为整个
那个叫什么？我喜欢就是因为这个宇宙是一个，让他把自己解释的更好，但是单纯的问问题的话，他确定说是不是对，他认为这个问题是中文是所以并不是说
对那个会应该会，如果你没有去设法让他不了解一个呈现，
说整个呈现下来多少，
一定的感觉上作用感一定有一点点
真的问题。对，所以说在发选的技巧上，对，再加强。
但是因为我都问了，我只是觉得说你变化面都没写出来，你要这我
你说简报内容，
你那个已经是更进一步了，你都没有写出运动化
内容，
你如果是你这个就
对，我没有太怎么在
这一定会影响事情的运动。
对，可能是，譬如说，尤其是第一场自己的句子就因为他一闪一闪的，我没办法看简报内容，所以就变成要靠别人的。对，因为我看有不稳定的。对，那别人可能也吓到了，所以但其实也不是讲，就创造学员没有把这个郑重
才可以用。
对，这是第一场问题。下次会再进行
就是也不要赶这边加水，反而会影响他的这个。
我等下就问一下他多高，又高又帅，
那肯定应该要带着。
湿哦，潮湿。没差，现在都读。哦，今天为什么不理我？好尴尬哦。
So the opponent can challenge to report a problem.
We challenge your problem H equipotential line.
Okay, problem accepted. Problem number 8, equipotential line. And so the representative, please.没关系，没关系。我再跟他们讲就可以了。林廷伟，中文，林廷伟，报告。
Hello everyone, my name is Xin We're from Shangzhi Shixing, and today I will report number 8, eco-potentialized. Here's the proper statements. You should place 2 electrodes into water, supply the voltage, and use a voltmeter to determine electric potential at various locations. In case that how to measure eco-potentialized differs from your expectation for different conditions and liquids. And I mainly focus on how eco-potentialized differs from our expectation for different conditions and liquids. It's my outline of the section. And here are our experiments, the basis for solution experiments. And we set voltage, the temperature of solution, the volume of solution, and the height in the solution of curve as our control variables. That's the basis of our carbon plant experiment. And according to this sample, you can see that eco-potentialized close to the electrodes is curved, and something will attach on electrodes. And we find out that the eco-potential that is in the middle is not straight. And overall, the eco-potential that are not symmetrical theory. And this is the schematic that explains why we use dynamic electricity in our experiments. On the left side is static electricity, and the right side is dynamic electricity. And the reason of that is because we cannot measure the electric quantity of static electricity, so we use dynamic electricity instead. As for why we can use dynamic electricity, simulate static electricity, attack parallel electrodes, for example, because in ideal, it will have electric field in a vacuum. And in real, electric field is produced by the flow of charges, so both of them have electric field. So the diagram is that 2-point charge with same charge, and R1 equal 2, and then the voltage will be 0. And the formula in the left side is for pull. As for this one, we'll start from 2D. According to Gusto, the electric field of 2D will be like this, and then go further to this step. And the voltage of 2D can be calculated. And the formula in the left side is for voltage of 3D. And then we can look at the electric field of 2D and 3D. They're both related to permittivity. If permittivity change, the electric field will change too. The formula is for Coulomb density. We can derive that Coulomb density, drift velocity of ion, and electric field have relevance. As for this part, we will talk about why eco-potentialized field expectation. Because every ion has different drift velocity in electric field and cause to the different Coulomb density, and that makes the ions are not uniform distribution, And finally, it is to defeat expectation. This is the chemical reaction of sealing. You can see that the negative electron will produce hydrogen, and the positive electron will produce oxygen and chlorine. The permittivity of gas is much different from the permittivity of liquid, so the electric field will also change. This is the chemical reaction of copper sulfate, and we can see that it will also produce hydrogen and oxygen. However, the amount of this is less than that of sealing, so the variation of electric field is smaller. Experiment and discussion. We use sealing and copper sulfate as our solution. Overall, we can see that the potential lies in sealing and copper sulfate are different, and there are two main reasons. And the first reason is that the velocity of every ion is different, so it's because the ions will not be uniform distribution. And the second one is that the variation of permittivity is different. We can compare the potential light that's close to anode and cathode. Obviously, those which close to anode is different. Besides, the potential light of copper sulfate is much different from ideal potential light. That's because the velocity of sulfate is faster, but it will not have reaction with other ions, so it will have too much sulfate deposit as a node. The potential light which close to cathode is faster and also much close to the ideal situation because the velocity of positive ion is slower. So the ions distribution close to cathode will not have that much of disparity as the anode is. And this experiment is for comparing the potential light for different concentration of sealing. We can find that there is apparent difference as the place close to electrons. The reason is that the velocity of chlorine and sodium are different, especially as the place of anode. The second reason is that intensity of variation to permittivity is not the same. The potential light of sealing in 0.01 molarity is symmetrical and ideal because the permittivity changes a little. This experiment is for comparing the potential light for different concentration of copper sulfate. We can find that there is apparent difference as the place close to electrons. The reason is that the velocity of copper and sulfate are different, especially at the place of anode. The second reason is that there are too much sulfate deposits at the close of anode. The potential light of copper sulfate in 1 molarity is not symmetrical and ideal because 1 molarity will have the most amount of sulfate and then deposits as a node. Next, we use carbon plates to do the experiment. You can see that the potential light and electric potential have symmetrical distribution. That is because no ion flow on carbon plates, and so it's called uniform electric field. Then we compare the voltage of different concentration of copper sulfate, and we can find out that the voltage that's close to electrode has an obviously difference because the concentration close to electrodes is higher than the middle part, so it has a big variation of voltage. And we compare the voltage of 2D and 3D. We find that the experiments that we do is approach to the best. And sealing has the same principle as copper sulfate. As provide the voltage in sealing. As provide why the voltage in ceiling change more than that in copper sulfide? I think because ceiling in 1 molarity, permittivity change the most, so it causes this to happen. We found out that the equipotential lights will change over time. So first of all, let's look at different concentration of copper sulfide. We can find out that there is a little change in copper sulfide. Because it's produced as gas, the permittivity change a little. But the equipotential lights of ceiling change a lot because that is because it's produced more gas, such as chlorine. Therefore, the permittivity change a lot. Conclusion. Solution concentration affects equipotential lights. Drift velocity and permittivity affect the result, and the equipotential light on carbon plate is symmetrical, and the electric potential that's close to the electrons is different, and the last one is equipotential lights change over time. Here's the reference. Thank you for your attention.
Question.
So my first question for you is, how do you plot out the plots you've shown in your PowerPoint? And what do the dots mean? Do they mean the point where you probe
like this?
Yes. What do the dots mean?
It's the electron.
I need the smaller dots on your graph. The green one, the blue one.
Oh, it means 0. And the blue one means 0.01 molarity of copper sulfide,
Okay, thank you. So why don't you connect the dots into a line? Is it because that there is going to be variation between the dots that you cannot predict or measure?
Because I think
Thank you. So can you tell me how exactly you probe the electric lines? How do you conduct your experiment? Do you have a graph paper under that? What is the base of your electric potential?
Like this, we fix the negative probe and move the positive probe and up and down, and when the multimeter is 0, and we record it.
Yeah, I understand. So there is going to be a time interval between each probe, correct? Time difference.
Yes.
Honorable judges and worthy opponents, I am the opposer for the problem 8 equipotential line. The focus of this problem is that they want us to interpret the differences between the theoretical value and the experimental value. They also want us to test out how different parameters would influence the result. So in theory, they talk about how different drift velocity will form different current density. Therefore, ions in the solution will not be distributed evenly. This deviates from their expectation. They test out different parameters, including different solutions, concentrations, and different time rates. For their strengths, they thoroughly tested different parameters, and they fully responded to the problem statement. And lastly, they also produced a constructive explanation of the differences. But for the weaknesses, they lack concrete evidence for their assumptions. They have high error values, they don't have enough experiments, and they ignore factors that do not only cause marginal differences. And lastly, they lack the experiments. So the reporters, they concluded that solution and concentration would affect the ultimate equipotential lines presented on the graph. And secondly, they said that carbon plate can make the graph more symmetrical. And lastly, they talk about how drift velocity and different permitted effects. And we would like to clarify this further in our discussion session. So now I would like to move on to the discussion. Okay, so I'm going to start with the experimental part of your presentation. So first of all, I would like to ask, how can you make sure that the solution, for example, the sodium chloride solution, is homogeneous throughout the entire solution? Do you have any testing values for this or any experimental results? Testing the concentration of the solution of every single point in your container.
Pardon?
So do you have any experimental result, or can you explain to me how do you make sure that every single point in the solution has the same concentration? For example, like homogeneously, the ions are homogeneously distributed. Thank you. I will move on to the next question. So you said the way you probe the solution is that you're going to use the multimeter and then test out different spots and then graph that onto your graphs. Is that correct?
Yes.
So do you consider the time differences? For example, if you're probing the left-right corner of the solution, the ions are constantly moving. The concentration is still moving. And when you get to the right corner of the container, the concentration of the entire plate is already different from the initial state of when you first start probing. So how can you explain this?
We take the CD for example, and because the electrode produce hydrogen and chlorine and oxygen. So it's the permittability of gas is not different than the permittability of liquid.
Okay, thank you. What I think your answer to my question is irrelevant. What I mean is the concentration of the solution in the container. So if you use sodium chloride, how can you make sure that the concentration when you first started probing is the same when you ended your probing?
No, we
So you cannot ensure that.
yes.
Okay, thank you. So now moving on to the next part. Here on your graph, you've shown that there are many different colors of dots and different dots. So what is the delta V, which means the difference in electric potential? What do these do they have an interval between these lines? Because presumably, if you want to draw a electric potential graph, it has to have different lines, and the difference between the lines symbolizes the difference in electric potential. So do you have graphical or numerical supports for the graph and the dots?
I think this one can be equal this one, and because the permittivity change and the electric field is changed too, so I think it's called the equipotential line change over time.
Yeah. So what is the experimental gap you take when you want to draw the line? For example, 0.2 volt. So what is the difference between the lines you draw if you do have a line? Okay, thank you. It's all right. Thank you. So I have another question about your container. So what is the height of the container? For the solution?
0.4.
So do you think besides 2D electric potential lines, is it possible that there is going to be 3-dimensional electric potential line within this entire system?
But I think this one can be proved. Our experiment is 2D.
Okay, so you think that this height difference, you did not consider 3-dimensional lines into your experiment. Is that correct?
Pardon?
So you didn't consider the 3-dimensional lines in your experiment?
Because we use 3D space, and then the liquid is higher than the electrode.
Okay, thank you. So can you move back to the formula, the page where you have the formula and theories?
Yes.
Yeah, can you tell me how you get the result of 2 pi f0?
Yes.
Yeah.
Just according to Gusto. Okay, just according to Gusto.
Okay, so so how did you guys define electric field? So how did you guys define this variable? Okay, thank you. So how can you assume that the electricity producer is long conducting wires? Is there any proof for this? Because the formula presumably originates from the fact that it is long conducting wires.
Sorry, can you say that again?
So how can you make sure that why can you make the assumption that the electric producer or the weight you're using is long conducting wires? That allows you to use this formula.
Maybe because I think the electron of 2D and 3D is different. So I wonder my experiment. So I wonder which one is my experiment. But the experiment results prove our experiment is 2D.
Okay. So moving on. So you said you tested out different parameters of different molecules. Is that correct? Okay. So did you guys take into consideration the atomic differences between each of the atoms? For example, between sodium ion, cation, and chloride anion.
You mean the velocity?
I mean, yeah.
Oh.
Caused by the difference in atomic.
First like this one.
Okay. So can you explain why the middle line of your electric potential graph?
I think it's maybe the error of instruments, like internal resistance of the multimeter.
Okay, thank you. So I would like to ask you a hypothetical question. So what would you think will happen when the distance between the two electrodes are expanded as far as possible?
Pardon?
So what do you predict the result would be if you separate the two electrodes as far as possible? So you have
I didn't consider that.
okay. So you did not consider. Moving back to the container use, do you consider that there is going to be an accumulation of static electricity on the walls and the surface of the container when you conduct the experiment? And how do you think that will affect your result? And did you guys take that into consideration?
I think it was influence on our experiments.
Can you give me the reason why?
I think the potential lies have
Okay. Thank you.
because the height.
Can you repeat your answer again?
Because I think the height of solution affects the result.
Okay. Thank you. So one last question is about your graphs. So what tools did you guys use to draw out the graphs?
Algebra and Excel.
Okay, thank you. So in conclusion, I think the opponent did not successfully respond to many of our questions. First of all, they failed to tell us what the difference of electric potential actually is in their graph and why can't they graph out or connect the dots into lines, meaning that they're not able to predict or mitigate the variation in the experiment and between the dots. And secondly, they also failed to tell us failed to answer a lot of other outside factors that may influence the results. For example, the atomic mass of different atoms, and also how the container is going to influence the results. And lastly, we think that they did not successfully prove to us why they can use they're able to use the conducting wires as the formula basis and their basis for their theory. Thank you very much.
Next question, and first of all, I'm going to ask the opponent about, because the solution isn't homogeneous, so doing a 3D experiment or consideration have much more error.
Do you mean that if we use a 3D
Yes.
model, we think that then the concentration in and of itself is already an issue that is very hard for us to solve in the first place. And we think that the 3D calculation, if we put 3-dimension lines into consideration, it is even going to magnify this variation in this error value.
Okay, I understand. This question is for the reporter. Can you please turn to page 7? Oh, sorry, is your computer some error or mistake? Okay, and do you guys remember that on page 7 there are the ideal graph of their meaning to okay, please turn to page 17. And this three picture is all this the same, so what did you consider? What is all the same? The ideal this picture, what is all the same?
Because I use the formula to get it.
Okay, so does the opponent think this have to always be the same?
No, we don't think that it always has.
What do you consider about in this?
We think that the factor of dielectric is going to influence the result of the ideal equity.
Okay, and did you see the viscosity of different kinds of liquid may affect this ideal picture?
I think in our ideal, and the permittivity and the iron and the permittivity.
Okay, and I know that. And please turn to page 7. Thank you. No, please turn to 11. Sorry. Yes. Can you explain this formula? This is a cross or a dot? So it's a mosaic. So this is a dot or a cross?
Sorry, yes.
And how did the opponent?
We think that it is not a cross, it should be a dot. So there is a mistake in their formula and their theory.
I understand that. And please turn to page 17 again. What's the x and y axis refer to?
Precision.
And sorry, can the opponent just guess what the y-axis and the x-axis is referred to?
I think they refer to difference in the
Okay.
Okay.
Thank you for the opponent and the reporter, and I'm the reviewer of one lecture of the 9120, and today I'm going to review this question. And here's the problem statement, and we main focus on how to measure the potential lines and different conditions, different locations, and different limits. And here's the pros and cons of the reporter and the summary. The reporter says that close to the electron curve will have bigger energy, or yes, and then she had five kind of in his theory, and the dynamic electricity and the potential, Coulomb's law, the gases law, and the current density. And page 16, it would produce the hydrogen. And here's the experiment that she did about the voltage measure and about the carbon. And here's the pros of the reporter. She has clear structure about his. Yes, clear structure, and he talked about the problem statement, observation, and he talked about theory, about the ideal, the theoretical, the expectation, and also the chemical reaction. And she did the experiment and point charge, and in the end, she did the conclusion. But there's no connection between the theory and the calculation, and lack of comparison of different parameters like the liquid that she did, and answer the wrong question that the opponent asked about, and also lack of the explanation of the phenomenon, and lack of constructive communication. Okay, and here's the pros and cons about the opponent. The pros of the opponent is clear point. She just pointed out why don't connection the dots, or how to conducting the experiment time and the time different. And she has great understanding of the report that the reporter did, and clear structure, good time controlling. And here's the points about they didn't mention the lack of the experiment because they just did a little bit parameters, and they spent too little time in the question, and she skipped a lot of questions. And she didn't have her own opinion, and lack of explanation of the phenomenon. And here's the discussion of their first question. The reporter said about the connecting the dots, and the reporter says there's no need to connect the dot, and the opponent says we have to connect the dot to a line. And in our opinion, we think we're able to connect the line because the dot is continuous, and we have to connect the line and make the report more perfect and improve the report. And here's the discussion of the solution of homogeneous, and the reporter says that didn't answer the question, and she didn't answer the question of the opponent, and the opponent says the concentration of the solution would change through time. So in our opinion, we think about the concentration is changeable, so it isn't homogeneous. And the third question, the discussion about is if the bar is far, and the reporter don't consider about this, and the opponent didn't give their own opinion about if the bar is far, and the reviewer we think about the potential line will be parallel. So okay, and here's the point missed and by the reviewer and the opponent and the reporter. And in page 11, the constant won't be when the solution is Vcom. So when it's not in Vcom, so it can be like writing like this. And here's the main point. Yeah. Thank you for listening.
The dot cannot be aligned because that the electric field has limit range, so we cannot measure. It. So that's why we think we cannot light it up. In the theory, there will not have ion source, so the electric field will not uniform distribution, and that won't produce gas. So the electric field will change. So the electric field won't change too. About the every dot has same concentration, we think that we cannot measure every place have same concentration. For example, the drift velocity of ions, so that's a potential light in theory. Thank you.
So, now the question from the juror. Anyone want to make some comments? Please.
Can any of you explain how you describe the electrolyte look like at the interface of the water and air? And how does it?
There's no answer. Nobody's answering your question.
I think it's
okay.
It's our fault. That's the solution, and it might have a potential like this in our theory.
We think that when at the interface between the water and the air, the electrical potential is going to decrease immediately because of the difference in dielectric and also in resistance.
And in our opinion, we think that because of the air is not a conductor, but the water is a conductor, so there may be an electric field on the water, but so that the electric field will be the same as in the air.
What?
Electrical field.
Electrical field in the air, which will be
Potential field.
Will these lines be perpendicular to the surface of the solution of the water? The line, electric lines in the air. I am following the question. For electric lines, the experiment shows that they are perpendicular to the equipotential lines, and so they sort of in the same plane and then going from one electrode to the other. Whereas in the air, you still have potential difference between the two electrodes and maybe between the electrodes and the water. Right? Yeah. So the electric lines from the electrodes to the surface of the water or solution. This is what the problem is about. Your expectation and what you measure. Right? Of course, you didn't measure the electric fields in the air.
In our opinion, we think that because the line is straight vertical to the water surface, so we don't have to consider about the straight potential.
Straight.
Yes, the
yeah,
vertical.
This is straight.
Lines.
Okay.
Yes, so
straight field lines.
We don't have to consider about this side.
Yeah, the surface is equipotential. Will you say? Probably not. Anyway.
Probably not. Yes, probably not.
I'm curious. What kind of theory of electricity are you using? A steady state or you seem to be using? You use Gauss's law. That's good for what? For steady field. Steady field.
It's for the electric field of
steady electric field. It is Coulomb's law. Anyway, the problem didn't ask you to work out a theory, just what you expect. Of course, what you expect usually is from your understanding of the theory. I think your time is about, that's about all. We will concentrate on giving you the grade. Are we all set? Okay, next. 5. Okay, you're not ready. 5, 4, 6, 5. Okay. For the opponent. 7, 7, 7, 6, 7. Okay. And then finally is for the reviewer. 7, 7, 8, 7, 7. Okay?
Thank you.
Right. Thank you. Thank you all. Thank you all. That's the end of this fight. Thank留在桌上。
Of course.